Hi everybody, this is Mr. Short. Today we're going to be talking about atomic structure, and in particular we're going to learn about a couple of definitions. We're also going to learn how to calculate the number of protons, neutrons, and electrons in atoms, ions, and isotopes. Before we get started, I want to make sure that you guys have a copy of the periodic table of elements. This is loaded up under modules in Canvas, so let me just scroll and show you where this is at. If you go to your Canvas page and click on modules, it's the second one down right there. And I think this is most important today because with the periodic table of elements, we're going to be taking a look at the atomic number, which is this whole number that on this periodic table appears on top of the element symbol. The atomic number tells you how many protons are inside the nucleus. So for example, nitrogen has 7 protons in the nucleus, but oxygen has 8 protons in the nucleus. So make sure that you've got the periodic table handy as we're doing this activity. All right. The other thing I want to mention is that I'm going to break this note session into 2 different videos. We're going to do page 1 in one video, and then we'll stop, and I'll make a second video for page 2. Okay, on page 1, what we're going to be talking about is atoms, ions, and isotopes. We're also going to be taking a look at a table about the mass, charge, and location of protons, neutrons, and electrons in atoms, ions, and isotopes. All right, as you go through, please feel free to either handwrite this if you want to download it and handwrite it, or you can digitally write this in just like I'm doing. So we need to describe atoms, ions, and isotopes. Atoms, by definition, have an equal number of protons and electrons. So I'm going to do all of my writing in red here. Protons and electrons. And therefore they have no charge. What we're saying here is that they've got an equal number of positively charged particles, the protons, and negatively charged particles, the electrons, and for that reason they have no charge. Okay, let's take a look at an example. We're going to look at potassium. Potassium on your periodic table is K, and its element number 19. And what that means is that neutral potassium atom would have 19 protons and 19 electrons. Okay, and because it's got an equal number of positives and negatives, it's going to have a balanced charge, and it's defined as a neutral atom. If we're taking a look at chlorine, chlorine is element number 17. So neutral chlorine atom would have 17 protons and also 17 electrons. Okay, that's the definition of atom. They're neutral. Ion. Ions, they have a charge, and the way that they get a charge is they've formed that charge by a gain or loss of electrons, never protons. Electrons, never protons. And so, for example, if we compare charged potassium ion with neutral potassium had 19 protons and 19 electrons. But what we're going to find is that potassium has this +1 charge. See the +1 in the upper right-hand corner. Well, the only way it can get a positive charge is by gaining or losing electrons, never protons. So because it's got a positive charge, and it can only gain or lose the negatively charged particle, it must have lost one of its 19 electrons. So it's going to have 19 protons, and it's going to have 18 electrons. So again, see how it's got fewer negatively charged particles, the electrons, which is why potassium ion has this positive charge right there. All right, if we do the same type of analysis for chloride ion, you can see that chloride ion has a -1 charge. Neutral chlorine, it had 17 protons and 17 electrons. Well, this is still going to have 17 protons, but because it's got a negative charge and it can only gain or lose negative charges, it must have 18 electrons. Okay? So you really have to stop and think backwards about the electrons and how the number of electrons relates to charge. If it's got a positive charge, it lost an electron. If it's got a negative charge, it gained an electron. Okay. Definition for the term isotope. So isotopes are different nuclear forms of the same element. So let's pause and think about the nucleus. We remember from the Rutherford experiment, the gold foil experiment, that the nucleus is small, dense, and positively charged. Okay, that positive charge comes from the protons that are in the nucleus, but you might also remember that there are neutrons in the nucleus. So by saying they're different nuclear forms of the same element, what we're saying is different isotopes of the same element are going to have the same number of protons, but different numbers of neutrons. Okay, so the proton number is going to stay the same, but they're going to have different numbers of neutrons. There's an announcement over the loudspeaker. Okay, here's an example, and we've got a nice picture down here. We've got so-called hydrogen 1, hydrogen 2, 2 particles in the nucleus, and hydrogen 3, 3 particles in the nucleus. The thing that's the same that makes each one of these hydrogen is the fact that they've all got 1 proton. There's the proton, there's the proton, there's the proton. The proton with this key is not filled in. But the one that's filled in, it's gray, that's a neutron. So you can see that hydrogen 1, it's only got 1 particle inside its nucleus, which happens to be the proton. Hydrogen 2 has 2 particles, one of which is the proton, and one of which is the neutron. Hydrogen 3 has 3 particles in the nucleus, 1 proton and 2 neutrons. Okay, so again, isotopes. Isotopes of the same element, they've got the same number of protons, but they've got different numbers of neutrons. All right, the reason that this is the element hydrogen is because elements are defined by their number of protons. And in just a second, what we'll do is we'll scroll over and just confirm that hydrogen is the element that has 1 proton. So this is defined by the number of protons. And again, if we go back here, you can see that hydrogen has 1 proton right there. One thing that I say that when we're in the classroom is that hydrogen would have 1 proton. If something has 1 proton, as each of these do, then it's going to be hydrogen. And if it doesn't have 1 proton, then it's not hydrogen. Okay, now we're going to take a look at the mass, charge, and location of the 3 subatomic particles that make up an atom, which are protons, neutrons, and electrons. Okay, for charge, we know that protons are positively charged. We also know that electrons are negatively charged, so I'm just going to put a negative sign in there. And we know that neutrons have no charge at all, so I'm going to put neutral, and then down below it, I'm going to put no charge. In terms of mass, the mass of a proton is equal to the mass of a neutron. Protons and neutrons each equal 1 atomic mass unit. Okay. Neutron is also 1 atomic mass unit, and the way that we abbreviate atomic mass unit is AMU. Okay, you might remember from the Rutherford simulation that the nucleus of the atom, as Rutherford found, is small, dense, and positively charged. When we talk about the density of an atom, we're talking about the protons and the neutrons that are inside the nucleus. Each one of those protons and neutrons, they each contribute 1 atomic mass unit to the mass of an atom, ion, or isotope, which is why we say that the nucleus is very, very dense, because that's where the vast majority of mass of an atom is located. Electrons, in contrast, are teeny tiny. The mass of an electron is only 1/2000 AMU. So let me put that into context. What this means is that it would take 2,000 teeny tiny electrons to equal the mass of either 1 neutron or 2,000 electrons to equal the mass of 1 proton. So for that reason, we typically don't consider the mass of an electron when we're thinking about the mass of an atom, ion, or isotope. Let me put this into context a little bit better. If you were to take out the calculator and type 1 divided by 2000 equals, it would equal this number right here. It's 0.0005 atomic mass units. It's really, really small, and for that reason, we don't think about the mass of an electron when we're thinking about the mass of atoms, ions, and isotopes. In terms of location, we already know, according to Rutherford's gold foil experiment, that the protons and the neutrons are located inside the nucleus. Okay, so the protons and the neutrons are located inside the nucleus. For right now, all we're going to say about the electrons is that the electrons are located outside the nucleus. Okay. Later on in the next section, which is going to be section 1.2, we'll better define where the electrons are at and what the electrons are doing. Okay, just want to hammer home two big ideas right here. You can see the guiding questions on the left-hand side over here. Question number 1 is, what's the charge on the nucleus? And again, we've talked about this, we've emphasized this a couple times, just want to make sure everybody understands. As determined by Rutherford, the nucleus is positively charged. The nucleus is positive because, the only charged particle in the nucleus is the proton. Because remember, the neutrons, which are also located inside the nucleus, they've got no charge on them, right? So again, what's the charge on the nucleus? Nucleus is positively charged because the protons are the only positively charged object that's inside the nucleus. All right, and then in terms of the question, what is the mass of an atom? Where is most of the mass of an atom found? Most of the mass of the atom is found in the nucleus for that same reason, as we're going to talk about in a second. Because this is where the two massive subatomic particles are found, and those two massive subatomic particles are the protons and the neutrons. Okay. All right. So that's the first half of this lesson. What I'm going to do is to stop and load up another lesson in just a minute. Thanks a lot. See you in a minute.